following presentation documents our team's final project for DSBA 6190, in which we developed an image classification model using Amazon SageMaker, which predicts distracted driver behavior. There are three main goals for our project. Develop a platform-as-a-service machine learning prediction model on a scalable platform that exhibits elastic scale-up. We've already discussed the model we created and the platform that we used. For elastic scale-up, we verified this by performing a load test of the deployed inference endpoint using the Locust open source tool. The following is a process flow of our entire project, which can generally be broken into three main steps: data processing and upload, model training and endpoint deployment, and the development of a REST API to access the deployed endpoint. Step 1. We'll start with our data, which was taken from the State Farm distracted driver dataset hosted on Kaggle. It provides images in 10 distinct classes, shown here. Here's an example image from class C8, hair and makeup. As a process, we download that data locally and then split it into a training and validation set. Then we convert those sets into a record.io format, which our algorithm prefers. Once converted, they're uploaded to an S3 bucket. Step 2 is where most of the work happens. Our source code is hosted in a GitHub repository, which is connected to a code build project. Once that project is triggered, it executes our source code, including a Jupyter notebook, which then accesses all our SageMaker resources. When that notebook is activated, it starts training our model using the SageMaker image classification algorithm. The trained model is then saved as a model, applied to an endpoint configuration, and then, if an endpoint exists, it updates that endpoint with our new endpoint configuration. If the endpoint does not exist yet, it deploys it for the first time. At that point, an auto-scaling policy is applied to make sure our endpoint can handle high loads and scale elastically. Step 3 is how we access our endpoint using a REST API method with Amazon's API Gateway and Amazon Lambda. It starts locally, where a local user would send an image to an API Gateway, which will transfer that image to our Lambda function. The Lambda function then uses the deployed endpoint and then uses the image as an input and receives back the probabilities that that image is in each of the 10 defined classes. It then returns those probabilities to the local user. As an example, here's how it would work in real life. The user would take endpoint, like our sample image, and send it to our API gateway, and will return a list of probabilities of what class that image exists in. You can see here, we know this image is class C8, the 9th, second to last class. And it shows here it has a 96% chance of being in that class. So it seems to be behaving as we'd expect. To verify elastic scale-up, we performed a load test. Our load test acted in a stepwise manner in which we added 400 new users, each requesting the endpoint about once a second, every 10 minutes. So we go from 400 to 800 to 1,200 users, requesting the endpoint roughly 1,200 times a second. The following graph exhibits the metrics provided by Amazon's CloudWatch, and we can see the amount of times our endpoint was invoked during this load test. The orange graph is the amount of times the endpoint was invoked per instance, whereas the blue is the total invocations overall. So you can see right around 1904, those two lines diverge, indicating our second endpoint has come online because our auto-scaling policy has told it to. The total number of invocations jumps up, but the number of invocations per instance remains steady, showing that the load is shared between the two instances, showing also that our auto-scaling policy does work and will automatically scale to match load. Thank you very much for listening. I hope you found this presentation interesting and informative.